So we've seen some of the ways that we characterize acids and bases quantitatively, finding pH and concentration of this and concentration of that, and we could compare numerical values of Ka to know what's a stronger acid, a weaker acid, that kind of thing. What about qualitative values of acids? What about their structures and characteristics of acids and bases structurally? So acids, Bronsted acids is what we will see most often, but the end of this video we'll talk about something else. But Bronsted acids must have a proton in the structure. If you don't have a proton, you cannot be a Bronsted acid. Okay, cool. There's a common Lewis structure setup for some organic acids. That's what we will call these kinds of things most of the time. Organic acids, where we've seen CH3, COOH. This guy is acetic acid. If you exchange that CH3 for a hydrogen, that's formic acid. You can put all kinds of things on this other side, but this grouping of a COOH is called an organic acid, and that's another characteristic of acids, a Lewis structure characteristic. Often, things that are cations are acids because they're very happy to get rid of an H and a plus charge. CH3, 3N plus H plus. Acids are often cations. They don't have to be, but they could be cations. See, this guy up here is not a cation, but it's still an acid. Okay. So, bases. Anions are often bases. We're going to, like I said at the end of this video, talk more about Lewis acids and bases, but Bronsted is where we're at now. Things that have negative charges are often willing to accept an H plus to bring their charge closer to neutral. Okay, cool. I said this before, and I think I'm going to have to say it a few more times. Neutral compounds that contain nitrogen are known as bases. For similar reasons, when you're in organic chemistry, you're going to talk about these functional groups a lot. This neutral nitrogen-containing compound, I probably shouldn't do this, but it's called an amine, and amines are bases. This lone pair on that nitrogen Lewis structure makes a big difference in how this thing behaves. Okay. So, if you're comparing two acids and you don't know their Ka values, again, quantitative, we've already talked about, versus qualitative is what this is about. If you're comparing two acids and you don't know which one is stronger, there's two main cases that should be considered. Case number one, where the proton, again, this is Bronsted, the proton is attached to atoms of different sizes. So if I do a little high-quality drawing up here of my little periodic table, if you have a hydrogen attached to atoms in different groups on the periodic table, so that's like F versus Cl. Isn't that super legible? Yep, F versus Cl. Those are different sized atoms. HF versus HCl. The proton is bound to a small fluorine because it's in period 2 of the periodic table versus a larger Cl because it's in period 3 of the periodic table. The bond length is very different in a HF versus an HCl. Longer bonds are weaker bonds. Weaker bonds make stronger acids, always and forever. Weaker bonds make stronger acids. You should probably write that down, and there's a reason I'm trying to say it super slowly. Strong acids dissociate completely because strong acids have weak bonds between their H and whatever it's connected to, like HCl, HBr, HI. Strong acids have weak bonds because which causes them to, let me say it that way, causes them to dissociate completely. The stronger the bond, the weaker the acid. Case number 2, the proton of the acid is bound to a similar sized atom. You have to look to other factors. So if I draw another little periodic table, that's like if you're comparing things across a period, like hydrogen connected to carbon versus nitrogen, or maybe oxygen versus oxygen. Those are definitely similarly sized. They're exactly the same. So case number 1, different sized atoms. That's when you're comparing something in a group. A period 2 versus a period 3 element. A period 3 element versus a period 4 element. That kind of thing. Atoms in the same period have similar radii. So carbon, nitrogen, oxygen, fluorine all have similar radii. So when they have similar radius, it's about electronegativity. So here, I've got hydrogen connected to oxygen versus hydrogen connected to carbon. Within this same molecule, I need to decide which hydrogen is more acidic, the one connected to oxygen or the one connected to carbon. Because carbon and oxygen are in the same group, they're in the same period, they have similar radii. So then it's about electronegativity. So the more electronegative atom is the stronger acid. So that means with these 2 hydrogens in HCO2H under consideration, this hydrogen that's in the blue circle now is much more acidic than the one connected to carbon. Okay, in the bottom element there's only 1 hydrogen, but it's that one that would be most acidic because it's connected to oxygen versus nitrogen in this bottom molecule. So then if I compare these 2 molecules, hydrogen connected to oxygen versus hydrogen connected to oxygen. When the hydrogen is connected to the exact same atom, you go one step further and compare the next atom. The next atom that you compare, it's still about electronegativity. So nitrogen is more electronegative than carbon, and you may not remember this. This is where I wish you could see my face, but I'm not about to turn on this camera. To be electronegative means selfish and pulling electrons toward itself. So the nitrogen starts to pull electrons toward itself. Yes, oxygen is more electronegative. But the nitrogen starts to pull electrons in that bond toward itself, which causes the oxygen to pull electrons in its bond to hydrogen, toward itself. So that makes this oxygen-hydrogen bond weaker than this. Carbon starts to pull a little bit toward himself, which causes oxygen to pull more toward himself. But this oxygen-hydrogen bond is weaker. You can't see my laser. This oxygen-hydrogen bond is weaker because the nitrogen is more electronegative. It's more selfish. It's pulling electrons toward itself more than the carbon is pulling electrons toward itself. The way we do that quantitatively with numbers in this class is with dipoles, dipole numbers. You might not remember, but back when you drew Lewis structures, there would be a dipole along this OH bond pointed toward the oxygen because oxygen is more electronegative. It causes the hydrogen to have a partial positive charge. That little delta, lowercase delta, means partial positive. It causes the hydrogen to have partial plus 0.4 and the oxygen to have a negative 0.54. If I compare the same sorts of things here, positive 0.44 versus positive 0.40, the larger the partial positive is, the weaker the bond is that's holding on to that hydrogen. Did you catch me? The larger that partial positive is, the weaker the bond holding that hydrogen. So it means this bottom acid is stronger than this top acid. This bond is weaker, therefore this acid is stronger. Larger Ka value, smaller Ka value, stronger acid. It's all about electronegativity. It's the electronegativity of the atom next door to where the acidic hydrogen is. Why? Because the atom that the hydrogen is connected to is identical in both cases. I know this has to be a very confusing thing. I've taught this many times and students get very confused. Case number 1, are your atoms the same size? If the answer, or similar size. If the answer is no, you're comparing things in a different group, it's about atomic radius. Bigger atoms, stronger acid. If your atoms are similarly sized, yea, though they're identical in our example here, if they're similarly sized, it is not about atomic radius, it is about electronegativity, and it is always asked in that order. First consideration is atomic radius, second consideration is electronegativity. Okay, let me be done with that. The more stable the conjugate base is, the stronger the acid is. So if this is super stable, it means it's very easy to form this anion. The more stable this is, the easier it is to form, the weaker this OH bond is over here. So this OH versus that OH, number one question, are those the same radius? Yes, they are the same radius. They're both oxygen. Number two question is, if they're similarly sized, they're both oxygen, it's about electronegativity of the atom next door. So electronegativity of sulfur versus carbon, who's more electronegative? Sulfur versus carbon. If I look at Ka values, I can actually answer that without much further consideration. So this number is larger than that number. Must mean sulfur is more electronegative than carbon. You can look up old electronegativity numbers to verify that to yourself. Maybe I should actually remind you of what the electronegativity pattern is. The most electronegative element on the periodic table is fluorine, and the trend goes toward fluorine. Electronegativity increases up and to the right toward fluorine. Sulfur is more electronegative, therefore H2SO3 is more acidic than H2CO3. Before we talk about the next subject matter, one more definition for you. These acids are called oxoacids. What are oxoacids? Oxoacids are often written as H, some element, a number of oxygens. H, some element, a number of oxygens. Okay. In oxoacids, the H's are often written first, like at the beginning of the formula, but the H is always connected to an oxygen in an oxoacid. That carboxylic acid structure that we saw just a moment ago, that's an oxoacid. An H, some oxygens, and another element. You can have lots of examples of oxoacids, and the rules we're about to go through are rules for oxoacids. So, oxoacids that have different central atoms, like carbon versus sulfur in our last example, that are from the same group, not like carbon and sulfur, and have the same oxidation number. Okay, let me explain. Chlorine and bromine are in the same group on the periodic table. They're both group 7 elements. When they have 3 oxygens on them versus 3 oxygens on them, that means it has the same oxidation number when they have the same number of oxygens connected. That's the shortcut way. Chlorine versus bromine, it's about the central atom's electronegativity. Because I am not going rogue here, hydrogen is connected to oxygen in both cases, so we have to look to electronegativity. Chlorine is more electronegative than bromine, therefore, here's my electronegativity chart that I was looking for, therefore, HClO3 is more acidic than HBrO3. HClO3 would be more acidic than HiO3 as well, right? Right. Oxoacids can have multiple oxygens, different numbers of oxygens around them. So here's hypochlorous. It's an oxygen with a hydrogen connected and another element. Oxygen with a hydrogen connected and another element. Oxygen with a hydrogen connected and another. These are 4 oxoacids of Cl and oxygen and hydrogen combinations. Hypochlorous, chlorous, chloric, and perchloric. You increase the oxidation state with each of those in that order. You increase the number of oxygens attached. Oxoacids that have the same central atoms but have a different number of oxygen atoms attached, the acid strength increases as the number of oxygens increase. So in that case, this one is my weakest acid in this table, and this one is my strongest acid. Oh, I've actually memorized. That's one of my 6 strong acids, right? More oxygens, so you can spread out that negative charge more easily in the conjugate base. That's a resonance thing. You don't remember Lewis structures, I know, but it's true. Here's a few Ka values for you. Proof that the more oxygens you add, the acid gets stronger. I didn't even give you Ka values there. This one has a very large Ka value, greater than 1 Ka value. More oxygens, more acidic. Okay, I feel like I'm on repeat here. Organic acids. We actually already said a little something about these. Organic acids. Look, all these things have the same connectivity of atoms. Those are carboxylic acids. You don't have to remember that. until you get to organic chemistry one day. But this connectivity is a very acidic thing, and you can have all kinds of different stuff attached on the other side. Carboxylic acids dissociate this way, and they make carboxylate ions. Maybe you've actually heard of that. That carboxylate can spread out that negative charge among both of those oxygens through resonance. You might remember resonance, you might not. It means move the pi bond to different places. That's the simplest definition I can talk about. But the more stabilized that negative charge is, the stronger that acid is. So carboxylic acids are relatively strong acids because their conjugate base is so stable due to resonance. That's the least organic definition I can give you. Sorry. What about bases? Well, we said this is all about structure today, and we said atoms that contain neutral nitrogens are often considered bases. Do you see all these little nitrogens I'm circling? They left a lone pair off of that one, and that one, and that one. We'll talk about those a little bit. Nitrogens that have lone pairs, nitrogens that are neutral, are often considered bases. They're in this table written in terms of base strength. So if you're talking about a Ka, this Ka is smallest, which means this base is strongest. This Ka is biggest in this table, which means this base is weakest, right? That's how acids and bases relate. Yeah. So we have been talking about Bronsted acids and bases, but we're about to talk about Lewis acids and bases. A Lewis base is an electron pair donor. A Bronsted base is a proton acceptor. A Lewis acid is an electron pair acceptor. A Bronsted acid is a proton donor. Both Bronsted and Lewis talk about acceptors and donors. If you donate a proton, you're an acid. If you donate an electron pair, you're a base. If you accept a proton, you're a base. If you accept an electron pair, you're an acid. So these are two different ways of defining the same things for the most part. What do I say for the most part? I like to think of them as a little Venn diagram kind of thing. All Bronsted acids are Lewis acids, but not all Lewis acids are Bronsted acids. Let that sink in. Similarly, all Bronsted bases are Lewis bases, but not all Lewis bases are Bronsted bases. So all the rest of this video was all about Bronsted acids and bases donating and accepting protons. But what if I expand my definition to talk about electron pair donation and acceptance? So Lewis acid accepts a lone pair. So this proton can be considered a Lewis acid, but it's also a Bronsted acid because it's a proton. So my oxygen that has electrons around it can donate electrons to my H, my proton, to make water. Electron pair donation, that is a Lewis acid-base concept in motion. This exact same example is a Bronsted acid-base example. This one is different. This one, nitrogen has a lone pair, so that's going to be the base because it's going to donate those lone pair electrons. It can donate them to boron because boron has less than an octet. And when it donates to boron, it makes a brand new bond between boron and nitrogen. And the organic chemist in me can't help but put these charges on here. You don't have to remember how they're made, but the organic chemist in me can't help it. So, base, acid, donor of electrons, acceptor of electrons, right? This is called a Lewis acid-base complex. There were no protons donated or accepted. So if I went back without too many clicks, if I went back to my Venn diagram, This top example, we'll put a star to represent it. This top example lies squarely in that egg yolk. It's a Bronsted and Lewis example. This, we'll put a star like this, belongs out there. It's a Lewis acid-base example that's not a Bronsted acid-base example. We're not going to talk a ton about Lewis acids and bases, but I have to feel good about myself for at least talking a little bit about it. Metal ions are often considered Lewis acids because they can accept electrons. So if I add something like aluminum 3+ to a solution of water, that aluminum 3+ can react with water's lone pairs. It can also react with hydroxide's lone pairs, like this. Hydroxide donates to the cation. Hydroxide is the base, lone pair donor. Aluminum is the lone pair acceptor. He's the acid. The equation would look like this, so that it accepts enough hydroxides to become a neutral compound. So if I have a solution and I add a bunch of aluminum cations to it, those cations react with hydroxide in solution, making the H+ ion concentration go up. So cations behave as acids in solutions, so they lower the pH of the solution to become more acidic. So if you just add aluminum to a water solution, if it was pH 7 before, and you add aluminum to it, that solution becomes more acidic. It's a weird little thing that we'll talk a bit about in a chem activity in the future. One more example, and then I'm done talking about this Lewis acid-base stuff. Lewis acid and bases, carbon dioxide and water. If you blow carbon dioxide into water, you can make that water more acidic because you create carbonic acid in there. Coke, like Coca-Cola products, have carbon dioxide in them. That carbon dioxide that you pump in reacts with the water to make Coke a very acidic compound, actually. There's other stuff going on in there. Got a lone pair, donate that lone pair to this carbon. Oh, bear with me. Carbon already has an octet, and he can't make more than 4 bonds, so I can move one of my pi bonds. Oh, I'm starting a little organic business here, but, bear with me. New bond is created between oxygen and carbon, and I've got a single bonded oxygen up there now. Let's make it neutral by grabbing an H and giving electrons back to that oxygen. That's how my carbonic acid is made when water and carbon dioxide come together. Yep, that's carbonic acid. This process is totally reversible. Carbonic acid can very easily decompose back into water and carbon dioxide. Carbonic acid has an organic acid, COOH kind of thing. Okay, I'm done. Lewis acids and bases are not a thing we'll talk a lot about, but I just have to feel good that we've talked about it at least a little bit, especially to know that cations, small metal cations, can increase the H+ concentration in solution, making the pH lower than 7 because they react with hydroxide in solution. That's all. Okay, that's all.